Welcome to EducAgent Studio, where a crew of AI agents help us teach, and you learn with ease. Here's the problem we'll solve today. Here are the vectors for parts A, B, and C. Each is written as a column vector. Decide whether each set spans a line, a plane, or all of our three. Pause and think. If you don't know yet, you'll feel great when we reveal the reasoning. For part A, we compare the two vectors and see that the second is 3 times the first, so they are linearly dependent. All linear combinations are scalar multiples of V1, so the span is the line through the origin in the direction of V1. So the span is a line through the origin in the direction 1, 2, 3. In part B, we form a linear combination A times Z1 plus B times V2. Note the X, Y, Z components in terms of A and B. Eliminating the parameter B yields the linear relation 3y equals 2z, which describes a plane through the origin. Because every linear combination equals A 2b 3b, eliminating parameters gives 3y equals 2z. The two independent vectors lie in and span that plane through the origin. Art C asks whether 3 given vectors are independent. We write the system for A, B, and C so their linear combination equals the 0 vector. Subtracting equations shows C equals 0, then B and A are also 0. Only the trivial solution exists, so the vectors are independent. Since the only linear relation is the trivial one, the 3 vectors are independent and together span all of R3. Let's recap our conclusions for each part. Part A. Both vectors lie on the same line, so the span is a single line through the origin. Part B. The 2 vectors are independent and span a plane given by 3y equals 2z. Part C, the 3 vectors are independent and together span the entire space. Great work! Watch the next video to learn more. There's always a fun geometric trick waiting. Welcome to EducAgent Studio, where a crew of AI agents help us teach, and you learn with ease. Here's the problem we'll solve today. Here are our 2 column vectors, V and W, given in component form. We will compute the sum and difference, then draw them all from the origin, and also show head to tail and the parallelogram rule. Pause and think. Can you predict where V plus W will land? If not, you'll enjoy the moment when it clicks in the next beats. First, we compute the component-wise sum and difference, so we know the endpoints. We get V plus W equals 2, 3, and V minus W equals 6, -1. These are the endpoints we will plot from the origin. We'll use a plane that contains all our endpoints, so the geometric relations are clear. We'll use this plane to plot the vectors and compare their endpoints and head-to-tail placements. We restate the vectors, so the viewer keeps the components in mind before plotting. Here are V and W drawn from the origin. V goes to 4, 1, and W goes to -2, 2. Notice their directions and magnitudes as given by their components. We will add the vector V plus W in 2 equivalent ways to emphasize component-wise and geometric addition. The component computation gives the endpoint 2, 3. We will show that vector geometrically as well. Method A. The sum V plus W is the arrow from the origin to 2, 3, matching the component calculation. Method B. Placing a copy of W at the tip of V lands at the same point, 2, 3. Completing the parallelogram shows the diagonal from the origin is the same vector V plus W. We will represent v minus w both as a component vector from the origin and via v plus negative w or tip-to-tip subtraction. The components give the endpoint 6 minus 1. We'll show this vector and two geometric interpretations. Method A. V minus w is the arrow from the origin to 6 minus 1, matching the component result. Method B, adding negative w at the tip of v, arrives at 6, negative 1, showing v minus w equals v plus negative w. Alternatively, the vector from the tip of w to the tip of v is the same as v minus w. This gives a tip-to-tip geometric interpretation of subtraction. Let's recap the endpoints and the geometric rules we used. All four arrows from the origin match these endpoints. We used component-wise addition, head-to-tail copies, and the parallelogram diagonal to see the same results. Great job following along. Watch the next video to learn more and keep the vector fun going. Welcome to EducAgent Studio, where a crew of AI agents help us teach, and you learn with ease. Here's the problem we'll solve today. Here are the two given vectors, v and w, each shown as a column vector. We will compute the specific combination 3v plus w and the general combination cv plus dw. Pause and think, how would you add scaled vectors component by component? If you don't know yet, you'll feel the satisfaction of learning it soon. First, we scale v by 3. Multiply each component of v by 3 to get the column vector 6, 3. So the scaled vector is the column vector 6 over 3. Now add w to the scaled v. Add corresponding components. 6 plus 1 gives 7. 3 plus 2 gives 5. Therefore, the components of 3v plus w are 7 and 5, written as the column vector 7 over 5. Scale v by an arbitrary scalar c. Multiply each component by c to obtain 2, c, and c. Similarly, scale w by d to get d and 2d as components. Add the scaled vectors component-wise to get a general result, 2c plus d for the first component and c plus 2d for the second. Let's recap the answers. Part 1. 3v plus w equals the column vector 7 over 5. Part 2. The general combination cv plus dw has components 2c plus d and c plus 2d. Thanks for watching. Watch the next video to learn more. Expect a playful follow-up with more vector practice. Welcome to EducAgent Studio, where a crew of AI agents help us teach and you learn with ease. Here's the problem we'll solve today. Here are the three given column vectors u, v, and w. We will add them and form a second combination, then explain a hidden dependency between them. The tasks: compute u plus v plus w, compute 2u plus 2v plus w, and explain why all three vectors lie in a plane by finding scalars c and d with w equals cu plus dv. Pause and think. If you don't know the answers yet, you'll get the satisfying insight very soon. First, add u and v component-wise to get the column vector -2, 3, 1. Adding w to that sum cancels every component, giving the 0 vector. So u plus v plus w equals 0. Double the earlier sum u plus v to compute 2u plus 2v, yielding -4, 6, 2. Adding w gives back -2, 3, 1, which is just u plus v. So 2u plus 2v plus w equals u plus v. From the zero sum, we rearrange to express w as -1 times u plus -1 times v. This finds the scalars immediately. So the coefficients c and d are both -1. Because w is a linear combination of u and v, all three vectors lie in the span of u and v. U and v are not scalar multiples of each other. Their components do not share a single scaling factor, so they are independent and span a two-dimensional plane through the origin. Thus, uv and w lie in that plane. Let's wrap up what we found. First key fact, the three vectors sum to 0. Second, 2u plus 2v plus w equals u plus v. Third, w is a linear combination with coefficients -1 and -1. Great job following along. Watch the next video to learn more about linear dependence, spams, and geometric interpretations. It'll be fun and a bit nerdy, and a bit Welcome to EducAgent Studio, where a crew of AI agents help us teach and you learn with ease. Here's the problem we'll solve today. Place the clock center at the origin. Each hour h corresponds to a unit column vector, v sub h at angle theta sub h equal to pi over 6 times 3 minus h. So 3 o'clock is at 0 degrees, and 2 o'clock is at 30 degrees. Here are the three short questions we'll answer. The total sum of the 12-hour vectors. What happens if we remove the 2 o'clock vector? And the x and y components of the 2 o'clock vector. Take a moment. Can you see any symmetry that might make the sum simple? If not, don't worry, you'll get the satisfying explanation shortly. Because the hour marks are spaced by 30 degrees, each hour has the directly opposite partner, 6 hours away. Pairing those cancels each pair, and the sum of all 12 vectors is the 0 vector. Each hour vector has a directly opposite partner 6 hours away. Adding each opposite pair yields 0, so the sum of all 12 unit hour vectors is the 0 vector. From part A, the total of all 12 is 0. Removing v2 means the remaining sum is minus v2. Since the vector at 8 o'clock is opposite to 2 o'clock, v8 equals minus v2, so the remaining 11 add to v8. Removing v2 leaves the sum of the other 11 vectors equal to minus v2, which is exactly the vector pointing to 8 o'clock. The highlighted v8 is the resultant of the remaining 11 unit vectors. With the plus x-axis pointing to 3 o'clock, 2 o'clock sits 30 degrees above that axis, so theta is 30 degrees or pi over 6, and v2 is the column vector of cosine theta and sine theta. Evaluating cosine and sine of 30 degrees gives the explicit components. The x component is √3 over 2, and the y component is 1/2. Quick recap of what we proved and computed. Part A, the 12-hour vectors sum to the 0 vector. Part B, removing 2 o'clock leaves a resultant equal to the 8 o'clock vector. Part C, the 2 o'clock vector has coordinates √3 over 2 and 1/2 as a column vector. If you enjoyed this symmetry trick, watch the next video to learn more. It's fun, fast, and occasionally clocky. Welcome to EducAgent Studio, where a crew of AI agents help us teach and you learn with ease. Here's the problem we'll solve today. We are given all linear combinations, c times the vector u plus d times v plus e times w, with c, d, e non-negative, and their sum at most 1. Shade the solid region of all such combinations. Then decide whether 1/2 of u plus v plus w lies inside that shaded pyramid. Pause and think. If you don't know the answer yet, you'll feel the satisfaction of seeing it shortly. First, we'll rewrite the constraints so the shape becomes clear. Introduce a zero coefficient, a0, equal to 1 minus the sum of c, d, and e. a0 is non-negative exactly when c plus d plus e is at most 1. Thus, every allowed vector is a convex combination of the 4 points, the origin, and the 3 vectors u, v, and w. That means S is the convex hull of the 4 points. Write 1/2 times the sum. It expands to 1/2 of each column vector. The 3 coefficients are non-negative, but add up to 3 halves bigger than 1. This solid is the convex hull of 0, u, v, and w. The tetrahedron S consisting of the interior and its 4 triangular faces. The centroid of the top face is the point 1/3 times u plus v plus w. It lies on the triangular face where the 3 coefficients sum to 1. The point 1/2 of u plus v plus w lies on the same ray as the centroid, but beyond the top face. So it is outside S because its coefficients sum to 3 halves, which exceeds 1. Let's recap the 2 key conclusions. First, S is the tetrahedron with vertices at the origin and the 3 column vectors. Second, the vector 1/2 times the sum of the column vectors is outside S because its coefficients violate the sum constraint. Nice work! If you enjoyed this geometric view of convex combinations, watch the next video to learn more. We might even build pyramids out of matrices next time. Welcome to EducAgent Studio, where a crew of AI agents help us teach and you learn with ease. Here's the problem we'll solve today. Here are our 3 given column vectors u, v, and w, and the target column b in 3-dimensional space. The goal is to find numbers c, d, and e, so that c times u plus d times v plus e times w equals the vector b. Take a moment. If you don't yet know the answer, you'll feel the satisfaction of learning it soon. We're about to work it out step by step. We equate each component of the linear combination to the corresponding component of B. Compute Cu plus dV plus EW component-wise. That gives 3 scalar equations shown here. We simplify the 0 terms to produce the final system. Next, we pack the column vectors into a matrix and group the unknown scalars into the vector x. We place u, v, and w as the columns of A, let x collect c, d, and e, and then the matrix equation, ax equals b, is exactly our system. We'll solve from the bottom up. Use the third equation first, substitute into the second, then into the first. From the third equation, we isolate d in terms of e. Substitute d equals 2e into the second equation and solve for c in terms of e. Now substitute c and d in terms of e into the first equation to find e equals 1/4. Finally, compute d and c from e to get the numerical values. We perform a brief check. Plug the found scalars back into the linear combination to recover b. Substituting c, d, and e and simplifying gives exactly the vector b, confirming our solution. So our solution vector x and the matrix A are shown here. The values match the check. A compact recap of what we did. First, we wrote the 3 component-wise scalar equations. Then we assembled A and solved A times x equals b to obtain the solution vector x shown here. Nice work! You just solved a 3x3 linear combination. Watch the next video to learn more.